Everyone, this is video 5, and today we're going to be talking about limiting reactant and theoretical yield. But before we start taking notes on page 159, I want you to go back to your Cornell notes from the last page we did, I think it was 153, and make sure you've done your revisions, questions, and summaries. Now remember, I want you to pause as I do this video and stop and take notes as we go. First, write down the essential question on page 159, and that's that I want you to determine the limiting reactant and theoretical yield of a chemical reaction from a balanced chemical equation and an initial quantity of each reactant. So let's look at an example. So given 6 wheels and 4 frames, how many bicycles can you make? The equation for this balanced chemical reaction would be that it takes 2 wheels and 1 frame to make 1 complete bicycle. Now, most new chemists have a very common misconception. They think that the limiting reactant has to be the thing that you have the least of. In this case, the least would be the 4 frames. But that's not necessarily the case. Instead, the limiting reactant is the thing that you're going to use up first. All right, so let's identify the definition of a limiting reactant. Limiting reactant is the reactant that is used up first in a chemical reaction, and it's said to be the limiting reactant. So it's not necessarily the reactant that has the smallest starting amount, but rather the one that gets used up first. So looking again at this bicycle example, even though we start with 6 wheels, the molar ratio of 2 wheels per 1 bicycle means that the wheels are used up first, and only 3 frames are required, and those produce 3 bicycles. So what ends up happening is you have 1 frame left over. And in this case, the wheels are the ones that are the limiting reactant. Even though we have more wheels to start with, 6 of them, they still get used up first due to the molar ratio in this example. All right, so we've determined that we're going to get, 3 bicycles out of this equation. But what is that called? Let's define theoretical yield. So the theoretical yield is basically the amount that you can possibly make given the starting amount of different substances. And it's theoretical not because it's untrue, but because it's mathematically the amount that you could possibly make. Now, in a lab setting, you may have some error that results in a smaller amount. So that's why we dub it the theoretical yield. And if you think about our activity today with the marshmallow sheep, some sheep legs were broken, or I'm sorry, with the marshmallow giraffes, some of the pretzels were broken, and it kind of messed up our yield. So if we look at the bicycle example, the theoretical yield when you have 6 wheels and 4 frames as reactants is 3 bicycles, because after making those 3 bicycles, you're basically all out of wheels. So it's really important to understand that theoretical yield and limiting reactant are totally interconnected. When you determine the theoretical yield, it allows you to determine what the limiting reactant was, and vice versa. All right, so we're going to set up a general procedure for solving theoretical yield and limiting reactant problems. And here it is. Step 1, you want to figure out what is your given and what is your find. Now always give you some amount of starting products. So let's look at this bicycle problem here. You were given 6 wheels as a reactant, 4 frames as a reactant, and you're asked to find some theoretical yield of bicycles or some amount of product. And I also want you to determine what substance is the limiting reactant. So that's step 1. What are you what are you given? What are you trying to find? Step 2, determine the mole ratios of each reactant to the desired product, and you get this information from the balanced chemical equation. So the mole ratios that are relevant in this case are the fact that there are 2 wheels, for every 1 bicycle. Also, you've got 1 frame produces 1 bicycle. Those are the 2 most important molar ratios in this problem. All right, so let's go to step 3 now. In step 3, if you need to convert between number of moles and mass, you would do so here. Now, in this example, this is just a kind of a mole-to-mole type calculation, wheels to bicycles. But if you're given the substance in grams, it may be necessary to convert from grams to moles in order to get a molar ratio amount. So in this example, step 3 is not necessarily applicable. So step 4 is to perform a stoichiometry calculation on each reactant that you're given. So let's start first with number of wheels. So I'm given 6 wheels in this problem, and I know that there's a molar ratio that says for every 2 wheels I'm going to produce 1 bike. So if I multiply 6 times 1 divided by 2, I get 3 bicycles, which you are probably able to do in your head. 3 bicycles. So in other words, I'm given enough wheels, 6, to produce 3 bicycles. Now let's look at how many bicycles I could produce given the amount of frames in this problem. So in this problem, I was given 4 frames, and it takes 1 frame to produce 1 bicycle. So I go 4 times 1 divided by 1, and then you see that I have enough frames to produce 4 bicycles. But I'm limited. I'm limited by this starting amount of wheels. I have enough wheels to make 3 bicycles and enough frames to make 4 bicycles. So what this means is that my theoretical yield, the amount that I'm mathematically able to make, it's only 3 bicycles. So 3 bicycles is my theoretical yield. So step 5 is basically to circle the determine the lowest possible amount of the product. I always circle it, and this is my theoretical yield. So that's what I did here. I've highlighted 3 bicycles. And then the final step is to take a look at the reactant that produced the lowest amount. And this reactant is our limiting reactant. So step 6, the reactant that produces the theoretical yield is the limiting reactant. Circle the reactant that produces the lowest amount, in this case wheels. So here I go. Wheels are my limiting reactant to produce 3 bicycles, my theoretical yield. Okay, so that is an example that we can use this procedure to do a real-life mole-to-mole ratio problem. So let's do one more example together. All right, for this equation, 8 zinc plus S8 reacts to form 8 ZnS. So if 2 moles of zinc reacts with 1.0 moles of S8, what is the theoretical yield and what is the limiting reactant? So let's go back to step 1 here. We need to figure out what is our given and what is it we're trying to find. So under the given column, I'm going to put these starting amount of each reactant. Under the find, I'm going to put the fact that I want to determine some number of moles of the product. And there's only one product in this case, 8 ZnS. So I got to figure out how many moles of the ZnS am I going to find. All right, so I've got a balanced chemical reaction. The other thing I need to figure out is what are the mole ratios. In other words, how much of each of these of this needs to react to produce this. So I'm going to write out those mole ratios here. It takes 8 moles of zinc to get 8 moles of ZnS, and it takes 1 mole of S8 to get 8 moles of ZnS. So let's set up our picket fence analysis. I'm going to need to do this twice. One for the Zn, and once again for the S8. Both of these are just one-step conversions. Should be nice and simple. So here I go. Starting with 2 moles of Zn, and given this mole ratio that says for every 8 moles of Zn, I'll produce 8 moles of ZnS, I take 2 times 8 divided by 8, and I get 2. 2 moles of ZnS. In other words, I have enough Zn to make 2 moles of this final product. All right, so that's good information, but we need to look at this other starting amount here, S8. Let's set up one more picket fence. All right, given that I have 1 moles of S8 to start, and I see from the balanced chemical reaction that there's a ratio of 1 mole of S8 for every 8 moles of ZnS, I can cancel out these two units and take 1 times 8 divided by 1, and let's see what I get. Oops. Oops. 8 moles of ZNS. So if I write this in plain English, it says, I have enough S8 of the starting reactant S8 to make 8 moles of ZNS. So you can see here that this 2 moles of the product is a smaller number than this 8 moles. So the smaller number is my theoretical yield. This is the only amount that I can mathematically make with this amount of starting ingredients. So if I look back to the reactant that I used that produced the theoretical yield, Zn would be my limiting reactant, and 2 moles of ZNS would be my theoretical yield. So I'll write that in here. 2.0 moles of ZNS is my theoretical yield, and my limiting reactant is this character right here, Zn. All right, let's write down one last thing here. The theoretical yield is the lowest possible amount of product, and the limiting reactant is the reactant that is used up first and produces that smaller amount, that theoretical yield. All right, so that's it for notes. I want you to practice 3 of this exact same type of mole-to-mole problem. So complete questions 1 through 3 on the limiting reactant and theoretical yield practice worksheet that you got today, and I'll see you tomorrow.